Here is example 2. This is the example about shear stress analysis. Okay, so here we have a handle shown below. It's attached to a 40 millimeter diameter shaft with a square shear key. That's a square shear key. Right, the forces applied to the lever are P equals 1.3 kilonewton. We have two P's. Okay, so if the average shear key, the shear stress in the key must not exceed 150 MPa, determine the minimum dimension A of the key if here should be the if the key is 25 millimeter long. That dimension has been summarized here. The L from here to here, this is the L, right? The L is 0.7 meter. Then the W, that is the length of the shear key, it's a 25 millimeter. W is here. Right? The D, diameter of the shaft, is 40. Right? The shaft here, this is 40. Right? Then the allowable shear stress is 90 MPa. So it's 150. Okay, so 150. This is wrong. Okay, so here in this example, let's do the analysis. Do analysis first. Right. So if you look at here, in this handle system here, when you load this 2 end with 2P, right? This lever will push the shear key. Will push the shear key in this way, right? So the shear key will give a reactant force to push the lever, right? Push the lever. This effective force will be shown here. This is how this shear key will push the handle to keep it equilibrium. Right? So if we do an equilibrium analysis, the free body diagram has been here, and we can write 3 equations. But here, actually, we only need 1. Right? We only need to analyze the bending moment. Right? So look at this system, and if the bending moment, sum of the bending moment, regarding to this central point here, sum of m equals 0. So from here we can get an equation that will be the P times its arm is half L, right? And we have 2 of them. Then the other one, if we call this F, the F will make a bending moment to balance the bending moment from these 2 P's, right? This is minus F times, what is the arm of this F? That should be half of the diameter of the shaft, right? This is half D, right, equals 0. From here, we can determine this F. And the shear stress, the shear force in this key, that will occur where? Will occur here, right? At the interface between this shear key and the shaft, or the bottom of this square, right? At the bottom of this square, there will be the interface of the shear, right? So we can also determine this area. The area will be W times A, right? We use this, the shear force V will equal F, right? Then the A is here, so the tau will be V over A or F over A. Right? This has to be not higher than 150 MPa. Right? So this is how we can solve A and then A, the small a. Right? This is the overall strategy. So let's see how to solve it in details. So as we mentioned, the first step would be free body diagram and then the equilibrium equations. We have written this equilibrium equation that will be sum of m equals 0, or P times L over 2 times 2 minus F times d over 2 equals 0. Right, so the F equals 2PL over D, right? So we have known all of these numbers. So 2 times 1.3 kilonewton, this is 1,300 Newton, times the L will be 0.7 meter. This is 700 millimeter. Right, Newton here. Let's use Newton and millimeter to get MPa directly. Right? So over 40 millimeter. Right. So here we can get this force that is 45,500 Newton. And as we have analyzed, the shear force V in the shear key will be the same as this F. That will be 45,500 Newton. And the area A is just W times A. And the W is 25, right? 25 millimeter. 25 millimeter times A. This is the expression of this area. Right, our tau can be calculated as V over A, and that is 45,500 Newton over 25A square millimeter. Right. So if we make this equal 150 MPa. Again, the Newton over square millimeter is equivalent to MPa. Right? So all of these units can be cancelled. Right? Can be cancelled. So after that, we can calculate the A. Right, the A will be 45,500 over 25 times 150. Right, so we can get 12.1 millimeter. So this is the size A determined from these numbers, but if you consider this as a design, so you should be clear that the larger the size is, the safer the structure will be. Since the larger this A is, the smaller the stress will be, right? So you will have more safety margin. So in this way, our reported results will be to determine the minimum dimension of A. The minimum dimension A will be 12.1. So if you report the results, you should say the A should be not smaller than 12.1 millimeter. Okay, so this is the correct engineering design report.